Thank you for watching my presentation. I am Kojiro Tanaka from University of Tsukuba, Japan. The title of my talk today is Intermediation Family, Workspace for Sharing Spatial Design Among Multiple Users. Recently, spatial design in a virtual space for multiple purposes. For example, spatial design systems can help designers to make room layout as shown the left image. Also, as shown the right image, some filmmakers use a spatial design to create movie scenes. In the future, more people will use the spatial design systems for multiple purposes. This slide shows the design process cycle. First, the design makes a first design with the spatial design systems, and the client and designer discuss it. Second, the designer modifies the design based on the idea and discuss with the client again. The design cycle is repeated again and again. Finally, the final design is decided. So, during this design cycle, it is important for the client and the designer to share the spatial design and its concept more deeply. However, it is hard to share the spatial design among multiple users with conventional design systems. Most spatial design tools are making tools for professional users, not for sharing tools. In other words, it is difficult for non-specialist users, such as clients, to use the tools well. Our proposal method focuses on this problem. There has been analog methods to share the spatial design. One of the traditional methods is an architectural model as shown in this figure. Although this method makes it easier to hold the architectural model in a client's hand and view it from various angles, it has some disadvantages compared to digital tools. For example, this method cannot give first-person perspectives and is not very realistic. In addition, the designer used a lot of time to make the architectural model. This research makes good use of the architectural model. 2018, Sugiyama et al. Proposed a system where an HMD user can share a spatial design among non-HMD users. The non-HMD users can control the spatial design through a third-person perspective using a touch panel. The HMD user can experience the spatial design through a first-person perspective. The non-HMD users can edit the spatial design based on the HMD user's opinions. However, it is more difficult to communicate to each other in this system than in the architectural models. It is because the experience of the HMD user and the non-HMD users are different. In other words, there are few research on sharing the spatial design in the virtual space with smooth communication like analog ways. In order to solve this problem, we propose a workspace for sharing a virtual space for smooth discussions about spatial design, using tangible interfaces and multiple perspectives. This workspace enables users, including non-design specialists, to communicate with others like analog method to discuss the spatial design. In this workspace, an HMD user and non-HMD users can share the interfaces to control virtual objects. Also, the users can get multiple first-person perspectives called FPPs and third-person perspectives called TPPs. In this presentation, we're going to illustrate the concept, the system, and the applications of this workspace. Now, we will show the introduction video of the workspace.
程よく頭出ててちょうどいいっすよ、サイズ感も。
Here, we will introduce the concept of the workspace and the interaction. We aim to create a system where users can control the virtual space like miniature models. And the miniature models, children and adults can share the spatial design and move miniature objects freely. So, we adopt the concept of the miniature models for controlling virtual objects. The workspace is composed of multiple tangible interfaces and a playmat to make the interaction of miniature models. The tangible interface is called the resident, and the playmat is called the floor. The users control virtual objects by moving the resident on the floor freely. The workspace consists of a real world and a virtual space. The dimensions of the virtual floor are the same with those of the floor, and the position of the virtual resident corresponds with that of the resident. By using the resident in the real world, the user can handle the virtual resident and the virtual space by three kinds of basic interactions: install, translate, and rotate. This means that even non-design specialists can move virtual objects easily, and the users can share the interaction each other. Next, we will explain the concept of the visualization. For discussions the spatial design, it is necessary to use both the first and third person perspectives. In this workspace, we can use multiple FPPs and TPPs using several kinds of displays. Especially, we can use two types of FPPs. One is a shared FPP and the other is an immersive FPP. Now, we will show the functions of these perspectives in the following slides. The shared FPP is suitable for the users to review the spatial design with others at the same time. As you can see, the virtual space through the FPP is displayed on the mobile display of the resident. By using the immersive FPP, the HMD user can observe the spatial design more immersively. The HMD user can set the viewpoint easily by moving the resident. The TPP is suitable for all the users to observe the spatial design as a whole, like this video. In this video, we used a small display on the table and a large display on the wall. Next, we will explain the system configuration. This figure shows the overview of the system configuration of the Intermediation Family. The virtual space is built by the Unity. The green area shows the functions for the interaction system, and the blue areas show functions for visualization system. First, we will explain the interaction system in the next slide. In the interaction system, the resident gets its position and direction on the floor and sends the data to the Unity. Then, the virtual resident is moved to the same position and direction on the virtual floor. The left image shows a general view of the resident, and the right image shows the details. The residence consists of a camera module, a computer module, a battery module, and a mobile display module. The photos illustrate the real modules. The camera module has a UVC camera to track the position and direction of the resident, and it has 4 LED lights to help the resident tracking. The computer module has a single board computer, Raspberry Pi. This module can calculate the position and the direction via image processing, and receive the image of the virtual space from the Unity and display it on this display. This is a battery module. The resident can run both wired and wireless. The mobile display module has a 5 inches display and shows a shared FPP. In addition, the module can be customized to characterize the resident appearance. Next, we will tell about the floor. In this workspace, we used an A0 paper as a floor. The encoded dot patterns are printed on the floor as shown in this image. The dot patterns are generated by libdot. Libdot is a programming library for tracking the resident position. We will explain the detail of the tracking library in the next slide. Libdot is a tracking OpenCV library using encoded dot patterns developed by Hastler et al. OpenCV with libdot calculates absolute position and direction using the image with an encoded pattern from the UVC camera, and the data is sent to the Unity. When the Unity receives the resident's position and direction, the virtual resident is set at the same position on the virtual floor. This means the users can control the virtual objects like miniature models freely. Next, we will explain the visualization system. The camera object of the virtual resident provides images built from the FPP to the resident and the HMD in real time. The camera object fixed in the virtual space provides images built from the TPP to the monitor on the desk or the projector on the wall. We used Unity render streaming developed by Unity Technologies for transmitting FPP images generated by the Unity to the display on the resident. Since the WebRTC technology is used in this streamer, although the computer of the resident is poor, it is suitable for sending images in real time. For the immersive FPP, we use the AirView software for transmitting FPP images generated by the Unity to the HMD. Since the HMD sends its orientation to the Unity, the HMD user can observe in any direction the user wants. The users can put the multiple camera objects in the virtual space for the TPP. The image is displayed in real time on the monitor on the desk or the screen on the wall. Here, we will show some applications of the Intermediation family. We developed two types of applications. One is a virtual walkthrough application to view the spatial design among the HMD user and the non-HMD users. And the other is a hands-on room layout application to edit a room layout in the virtual space easily. First, this is the virtual walkthrough application. In this application, the non-HMD users can share the spatial design views and control the virtual resident like miniature models. The HMD user can also experience the spatial design and communicate with the non-HMD users like this video. the virtual resident corresponding to the resident plays as the camera object in the spatial design, and the style of the virtual resident can be selected from two forms, a human avatar or a resident avatar, as shown in this figure. As shown in this figure, the users can observe the virtual space through the dynamic FPP by moving the resident freely, as if they were working in the spatial design. And the users can share the dynamic FPP and the resident interaction. This function allows the users to discuss the spatial design smoothly. In addition, the HMD user can experience the spatial design and share the design with the non-HMD users. As shown in Figure A, the immersive FPP can share the viewpoint with the shared FPP, so the non-HMD users can see what the HMD user experiences. And as shown in Figure B, the user can hand over the HMD to the non-HMD user easily. This also makes the discussion between the HMD user and the non-HMD user more smoothly. Moreover, since the height of the camera object can be changed, the users can also experience the difference between the adult FPP and the child's FPP in this application. This function is useful for the multiple users to observe the spatial design where adults and children coexist, such as a kindergarten and a house for a family. Now, we move on to the second application, the hands-on room layout application. In this application, the users can make a room layout like a dollhouse. Even non-design specialists can create a room layout in the virtual space, so it is easy for the users to give their ideas about the spatial design to the designer. As shown in the right image, each resident in the real world corresponds to the virtual function model, and the left image shows that some users can move the virtual function models using some residents. By moving some residents, the users can try several different spatial designs through the TPPs. The TPP can show the positions of the functional models and the appearance of the instant room layouts to the users. Of course, the users can observe the room layouts through the shared FPPs and the immersive FPPs. Now, I'd like to sum up my talk. We proposed a workspace to share a spatial design among users using tangible interfaces and multiple perspectives. In order to share the spatial design for non-design specialists, we've developed the workspaces system and applications. Currently, only a few participants have tried the workspaces applications. They had fun to experience our system and say that they could share the rich information about the spatial design easily. However, we haven't conducted a qualitative user evaluation. Moreover, when the user moves the resident quickly, the position and orientation of the virtual resident sometimes jump. In the next stage, we are planning to have evaluations focusing on the usability of the workspace and to make the resident tracking quality better. That brings me to the end of my presentation. Thank you for your kind attention.